guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about another kind of generative models, which is called Gans or Generative Adversarial Networks. Last session we talked about VAEs or variational autoencoders, which try to model the distribution in an explicit way, but the Gans or generative adversarial networks try to model the distribution without explicitly define a density function. And so we want to talk about GAN in this session. Okay, so in fact the problem that we want to solve is that we want to sample from a high dimensional distribution. In fact, each image, let's say, have some pixels, and if we call it x11 to x and n, then we have the joint distribution. And if we want to generate new images, then we should sample from this distribution. And because of the high number of pixels, so the dimension of this distribution is so high, and so this distribution could be very complex. Okay, so there is no direct way to do this. So another solution to solve this problem is that we could sample from a very simple distribution like a Gaussian distribution or random noise. Then so we sample from a Gaussian distribution. Let's say it is in one dimensional case it is like this. So we sample from this distribution, then we try to apply a transformation to generate this distribution. Okay, so we try to sample from a simple distribution, but by a complex transformation we try to convert that into complex transformation, complex distribution. So to use a transformation, one possible way is to use convolutional neural networks or neural networks to learn this transformation. Okay, so the duty of the neural network in here is to transform the simple distribution into complex distribution of the data. Okay, so we call it the generator network. So we have simple distribution in the input. Let's say it is a random noise or Gaussian distribution. From a Gaussian distribution we have some samples, and after that we pass them through a generator network which tries to apply a complex transformation of the input to data, and then create image with this network. Okay, so in Gans we have two networks. The first network is called generator network. The generator network tries to fool the discriminator. So we have some random noise from in here, and after that we want to generate some fake images or generate some images that are similar to the real images or the images of the true distribution. So this is the duty of the generator network, to create some fake images. After that we have a discriminator network, and the discriminator network could tell whether the input image is fake or not. So if the images are from the Gans, are from the generator network, then the output of discriminator will be fake, and if they are from the real distribution, or if they are real images, then they will be real. Okay, so we have this configuration to train the networks. Okay, so these are generative adversarial networks. Okay, so each network is like this. So the generator network takes noise as the input, then generates some samples. On the other hand, the discriminator network takes a sample and tries to classify that as a real or fake. So with this configuration and defining suitable loss function, we could train the network such that, let's see in here, we want to have realistic image, so that comes from the true distribution or data generating distribution. So in that case, the generator try to if we will see the cost functions in the next slides, but so the generator network tries to generate some samples that are really close to the real images, and they are really similar to the real images. But on the other hand, the discriminator tries to discriminate between the real images and fake images. So this is actually two-player games at the same time. So the generator network tries to fool the discriminator network, but the discriminator network wants to make itself more powerful to be able to discriminate between the true distribution and the fake distribution. So let's see how we could do that. So we could define the cost function of the discriminator network something like this. So we want to have the maximum output for the samples from the true distribution. So this is, as you could see, this is the first term in here, so we want to maximize this. So this is the first term. The second term is related to the samples that are come from the generator. So you could see that this is the expectation over z, which is this random noise in here. So we want the discriminator to have the output near 0, then we have fake samples. So we want to in fact we want to minimize this or maximize this one. Okay, so G of Z is the output of the generator network, so, and the D of G of Z is the output of the discriminator, which could be the probability of the real or fake, so it is between 0 and 1. And for the fake samples, we want to have a discriminator that tells us that fake samples are close to 0. So in that case, we want to maximize also this term. Okay, so in fact, for the real samples, we have this term that we want to close the output of the discriminator to 1, and we have another term for the generated samples, which are fake images, and we want to the discriminator to have 0 probability for them. Okay, for the generator we want to maximize this. In other words, the generator wants to maximize the output of the discriminator. In other words, the generator wants to fool the discriminator. Okay, so the generator wants to maximize this term, but the discriminator wants to minimize this. Okay, so this is a two-player game. Okay, so if we show the discriminator with a network, with a neural network, and let's say that neural network has some parameters or some weights, let's call all of them theta d, and for the generator we could define a network which has some parameters, let's call them theta g. So we want to find the optimum thetas as such that they maximize these functions, okay, that we define them. So now you know everything about these cost functions. Okay, so again, the generator network try to with this definition of the cost functions, the generator wants to fool the discriminator by generating real looking samples. On the other hand, the discriminator network wants to discriminate between the real or fake samples. So we could write it in just one term. So as you could see, we want to minimize this with respect to the generator parameters. In other words, so minimizing this with respect to the generator parameters is just means that this term, because just this term has parameters of the generator network, this term is independent from generator parameters. So in this term we want to minimize this, or in other words, we want to maximize this. Okay, so instead of writing maximizing this, we write minimize this, and the discriminator wants to maximize this, which we talked about this in the previous slide. So this is a min max game. So as you could see, we have a minimum, we have a minimization, and here goes on, and we have a maximization, and we should do this simultaneously. So this is a min-max game. Okay, so to solve this problem, we should jointly train this network. So we could not first just maximize this and then minimize this. Okay, so we should train this jointly. Okay, so we should train both of the networks at the same time. Okay, So as we talked about it, the discriminator wants to estimate the probability that a sample come from the true distribution or the training data rather than G. So it wants to tells us how much an input is a real looking, okay? And so we want to solve this problem, okay? To solve this problem, we want to, in other words, to minimize this thing with respect to parameters of the generator network and maximizing with respect to the discriminator parameters. We could alternate between these two simultaneously. So in the first step, we use the gradient ascent on the discriminator to one step try to maximize this, okay? So we use a gradient ascent step to maximize this. In the next step, we try to minimize this or use gradient descent on generator, okay? So we have a two-step training. The problem of this is that, let's see in here, the problem of, so this looks fine, but in fact the problem of gradient descent on this is that if you plot this term, you could see that it has something like this. It has this shape, okay? And the problem is that most of the times you are in these regions, and so using gradient descent means that you want to calculate the gradient of this. So and in here we have a near flat region, so the gradient is near to 0, and so you have not a proper update for your generator parameters, and this could slow down your training process, okay? And in fact your generator update will be poor. To solve this problem, instead of using gradient descent, we could use gradient ascent on this. So instead of having let's see in here, instead of having 1 minus the discriminator output for the generator, we now have maximizing with respect to the generator parameters of the discriminator output. So we don't have, so these are equivalent, but as you could see, we have a really better gradient in this region, okay? So now the updates for the generator will be better, and so it is actually more standard in practice to use to maximize this. So we could use the gradient ascent also on the generator. Okay. So to put it in a nutshell, we have you could see that we have something like this. So we have a random noise, then we sample from that simple distribution. It could be Gaussian. After that, we have the generator network, which try to transform the input, the noise, to generate a sample. So it could be a convolutional neural network or a neural network, and after that we pass this generated sample with some batch of sample from training data to the discriminator network and to train the network. Okay. After the training process of the generator and discriminator, our purpose was to generate samples from the input distribution or from the training distribution. Okay, so now after the training we could just use this part to generate samples from the true distribution. Okay, after training the GAN, so we could just use the generator network with some random inputs to generate some new samples. So you could see how we train the network, the discriminator and generator network in here. So for k steps, we will talk about this k in the next slide, but for k steps we first sample from the noise distribution. We call it Z1 to Zm, with the prior, which is probably a simple prior like Gaussian distribution or other simple priors. And after that we also sample a mini batch from the training data, which are from the data distribution. And after that we update the discriminator by using the gradient ascent on the discriminator. So after updating the discriminator, so as you could see here, we calculated the gradient with respect to the discriminator parameters. So we update first the discriminator, and after that we again sample a mini batch noise from the noise distribution. So we have again a sampling, so we don't use the same samples in here. We again sample a mini batch from a noise distribution, and after that we update the generator with stochastic gradient descent. So as you could see here, we have the gradient with respect to the generator parameters, and after that, so I'll update that. Okay, so the k steps means that, as you could see, the update of discriminator is in another loop for k steps. Actually, one possible approach is that k is equal to 1, means that for every time we update the discriminator parameters, after that we update the generator parameters. Okay, but some recent papers like as you could see WGAN found out that maybe other k also perform good on to update the discriminator and the generator. So there is no definite rule to how to choose k, but there are some experiments on the k to how to determine that, to have a stable training process. Okay, so these are some generated samples with Gans. So in DCGAN, or deep convolutional generative adversarial networks, it is good to know that the training of the GANs are so hard, in fact, in terms of the stability. In other words, the training of this two-player game training is kind of unstable. In most of the times, maybe it is unstable. So there are lots of different maybe tweaks or tricks to make the training of the GANs more stable. So training of GANs are much more difficult than the training of the convolutional neural networks, because they have two different networks that each of them wants to fool another one, and so they are adversary to each other. So training of GANs is kind of harder than training of convolutional neural networks. So there are some tips to use them when you want to create these GANs. So for example, in pooling layers, in these GANs, it's better to not use pooling layers. Instead of that, you use strided convolution. So you use the strided convolution for the discriminator, and fractional strided convolutions for the generator. So these are mostly experimental results instead of theoretical proofs for them. Or it's better to use batch normalization in the generator and discriminator to have better training and more stable training. Or remove fully connected hidden layers for deeper structures. As you could see also, we have it is better to use the ReLU for the generator, except for the output, which use tanh or tangent hyperbolic to get the output. And for the discriminator, it's better to use leaky ReLU. So these are not maybe the most or the best rules. Maybe you could create a network which ReLU in the discriminator is better than leaky ReLU, but this is a general guiding rule or general rules of thumbs to train a DCGAN, or to start to design a DCGAN. Okay, so this is an example of the architecture of the generator network. So you could have a noise in here. So this is a 100-dimensional Gaussian noise in here, and after that you reshape it and try to apply convolutions in different stages to generate your image in here. Okay, so this is GZ. Also, you could have conditional GAN, as we have the very pretty similar thing in VAs or variational autoencoders. We saw how to condition a variational autoencoder for the input. Also, we have a similar thing for the GANs that we could use to make them conditional. So this is a conditional GAN that is trained for MNIST. We have 0, 1, 2 to 9. So these are the generated samples of that GAN. And so these are some generated samples by Gans. As you could see, these are very realistic samples generated by Gans, and so this is so maybe surprising for you to for Gans to have such kind of sharp and crisp outputs. Okay, so let's talk a little about that latent space, or the Z, which is the first layer. It is kind of interesting. So let's say these are some woman's face. So the related noise samples that generates these, let's say these are Z1, so the average of these, so because the generator network that creates this phase is probably like this. So we have the random noise, and we have generator network, and we have this output. So let's call it Z1W, Z2W, Z3W. So if we use if we just calculate the mean of this, let's call it ZW. If we do the similar thing for, so these are smiling woman, so let's call it SW, and for neutral woman, let's call it ZW, and for neutral man, let's call it ZM. So the interesting thing in here is that if we subtract this ZW from the smiling woman, and then add the man latent variables to that, we could, and after that pass it to the generator network, we could get smiling man. So this is so interesting to see this example. So in fact, they have kind of, we could have some kind of vector arithmetic for visual concepts. So we have smiling woman, we subtracted neutral woman from it, and after that add neutral man to it to get smiling man, and that is interesting. And as you could see, we have some other examples that maybe looks interesting. Okay, so now let's talk about a little more about Gans. So for a fixed generator, so when you have a fixed generator, the optimal discriminator, so when you have a fixed discriminator, you could optimize you can optimize this with regards to the D, which is the discriminator, and in that case the discriminator, the optimal discriminator, so you should put the derivative equal to 0 and to get the discriminator, and the discriminator will be the distribution of the data divided by the distribution of the data plus the distribution plus the probability of the generator network. And when you have a generator network that that is creating new images, then your training distribution will have the same amount probably as your generator distribution. Okay, so in fact, in that case, if you have this equality, then the discriminator will be, so this is the optimal discriminator. So in that case, the optimal discriminator output will be 1/2. And in fact, in this case, for 50% of data which comes from the true distribution, the discriminator could tells us correctly, but for fake samples, it actually it will be fooled by the generator. Okay. So also you could use GANs in other applications like speak or speech synthesis or text generation or text to image generation and other different architectures to use GANs. And there are lots of variants of GANs which you could read the papers about them. And so this is a very hot topic in deep learning, that you could use GANs more. In the next session, we will see practical examples of VAE and GANs in Python and how to use them. But as a general suggestion, when you want to create a GAN, maybe, and especially if you are beginner or newbie in this GANs thing, it is better to maybe clone a project from GitHub and then see the architecture of the network and try to change that or make some difference in the architecture if you want to build a new architecture. Because as I mentioned, creating an architecture design from scratch maybe is hard. In fact, in terms of training, it makes your training probably unstable if you don't know exactly the setting or the suitable setting for that. So hope to now you know about GANs and VAs and generative models, and hope to enjoy from this session. So see you in the next session. Bye.